Good morning. Today I am going to talk about something that seems to be entirely different from the previous chapters within this textbook. That is because I am going to start the discussion with the color of light. In the following graph or the following picture from YouTube, we have the electromagnetic spectrum up here. And what you see is, well, all the colors of the rainbow that can be seen. And the table below, we have for each color the wavelength, the frequency, and the photon energy. So, what is a photon? In the late 19th century, people figured out that it was only possible to describe electromagnetic radiation properly if we assumed that light gets sent out in discretized energy parcels called quanta. Now, for light, these energy quanta are called photons. So the assumption was made that every time that you wanted to send out violet light, you had to send out a light particle called a photon with an energy of about 3 electron volts. Every time that you wanted to send out a light quanta of green color, you had to have about 2.3 electron volts. Remember that electron volts is a unit of energy. 1 electron volt is about 1.6 times 10 to the minus 19 electron volts. It turns out that we can actually test this in the laboratory using light emitting diodes. And for that I have a little video here.
We have here a little experiment with 5 light emitting diodes, and we are going to apply the same voltage to each one of these 5 LEDs. We're going to see when do the different LEDs turn on. So I'm starting to increase the voltage now, and as I increase the voltage, we start to see that the red LED starts to emit some light. So roughly here the red LED starts to emit light. That is at 1.66 volts. If we increase the voltage further, we also get a little bit of emission from the yellow LED. Now I'm going to switch ranges. As we increase the voltage further, eventually the green LED starts to emit light. After the green LED starts to emit light, we increase the voltage further. Okay, here I have to switch ranges again. So there we start to see some light coming out of the blue LED. Now I'm going to increase the voltage further. Now we also start to see some light from the violet LED. Strictly speaking, this is an ultraviolet LED, and so our eyes see very little of it, roughly at this point. We now can take these different voltages at which the LEDs have turned on and look at what photon energies they correspond to.
Okay, so you've seen the little experiment with the energies, and we can add our energies or our voltages that we have seen to this table. Let's see where we end up with this. For red light, we recorded about 1.5 volts before the LED turned on. For the orangey yellow light, we recorded 1.7 volts. For the green light, we saw that green light start to be emitted at around 2.0 volts. For the blue light, we started to see that turn on at about 2.4 volts, and the ultraviolet LED started to turn on at 2.9 volts. So we see that there's a pretty good agreement in the trend between the voltages that we needed to turn the LED on and the energy that the table told us that photons have. Now, you see that they don't line up entirely. Let's discuss why that is. First, the question, why do these voltages line up? The way the LED works is that you apply a voltage, and this voltage corresponds to the energy of electrons that get injected into the LED. If you attempt to inject electrons with a very low voltage, then these electrons will not be able to create photons. Why? Well, the energy for the photon has to come from somewhere. And if we don't give the electron enough energy in the beginning, we cannot get the photon out. However, once we provide sufficient amount of energy, then photons can be created from the electrons. However, the color of the photons is set by the device structure of the LED. Now, the device structure and some physical effects that I don't want to discuss right now also provide a tiny bit of a boost of the energy of the electrons. And that's why our voltages that we record over here are always around 0.2 electron volts lower than we would think they should be if we were just going by the color of light. So we now have a link between the fact that light is quantized and that the color of light corresponds to the energy of these photons. LEDs don't seem the most fundamental light source in the universe, so let's look at other light sources. The first video that I have is one where we look at sunlight.
Hello, I'm here in the heart of the physics department, and today is a beautiful sunny day, and that means that we can look at what kind of colors are contained within sunlight. For that I have a diffraction grating, and you can see as I go around the room that the lights come up in different colors. And so let's look what is inside sunlight. So what we can see here is that sunlight has all the colors of the rainbow in it. There's violet, blue, green, yellow, orange, red, and, well, very deep red.
As we have seen, sunlight contains all the colors of the rainbow, all visible colors. Light sources that behave like this are called thermal light sources. The sun is a thermal light source. It emits light because it is very hot. Old-fashioned light bulbs, Edison light bulbs, were also thermal emitters. They were heating a filament to a high temperature, and the high temperature caused the filament to glow. These days, of course, nobody uses these anymore. We all use light bulbs or light sources that stay cool. These light sources emit light because of the transition between electronic levels. One example is a fluorescent light bulb. Let's see what the light is that comes out of a fluorescent light bulb.
I'm now inside a physics laboratory, and up there is one fluorescent light bulb, and we can look at what kind of light comes out of a fluorescent light bulb. What we see here is that instead of seeing a continuous streak of colors like we had seen with the sunlight, apparently there is one copy of light that is blue, one that is cyan, one that is green, one orangey yellow, and one red.
So what we saw there was that a light that is emitted by a fluorescent light bulb has discrete colors, discrete energies. This was made into a model of the energy levels of an atom in the late 19th century through a following process. So let's look at the process of emission of light. Let's assume we have an atom that has three energies that we should label levels 1, 2, and 3. And we assume that initially our atom is in such a state that the electron sits at energy level 3. We then can think about what kind of transitions would this electron have. The first thing that it could do is it could go a very long distance and it could send light out. The photon energy of this light is exactly the difference of the energies of the electronic levels 3 and 1. However, that is not the only transition that is possible. For instance, one could go from level 3 to level 2. There we would also get emission of light, and the energy of this light would be the difference between the energy levels of the third level and the second level here in our diagram. However, now that our electron is sitting at level number 2, it's not done. It could, in principle, also decay to the level that we have labeled number 1. And so the energy of a photon that gets emitted to that process would be equal to the energy difference between the second level and the first level. So if we have an atom that initially has its electron in the third energy level, then we could get 3 different colors out. And the red and the green light energy would add up exactly to a blue light energy. Now we need a little bit of language here of what these things are. One would be called the ground state. The ground state is the energy level that the atom has if it has absolutely no energy. It cannot go any lower than that. Number 2 would be the first excited state. Number 3 would be the second excited state. So this is what emission looks like. Turns out that everything could also go backwards. That means that we could absorb light. Absorption in our energy diagram would be drawn as follows. Initially, a cold and unexcited atom would be in its ground state. If the atom would be very hot, it could be that some atoms inside the gas are in the ground state, some atoms are in the first excited state. The energy difference that you can get out of thermal excitations will be on the order of 1/40th of an electron volt. We have seen that these distances here typically are on the order of electron volts. So thermal excitation could normally not excite an electronic excitation. So initially, in a cold gas, we are in a ground state. Now, we send in photons of a certain light. Let's say we send in a blue photon. If we send in a photon that has exactly the correct energy for going from the ground state to the third excited state, then this is exactly what will happen. We'll take our electron from the ground state and send it up all the way into the second excited state, into the state with label number 3. Right now I have drawn everything without telling you anything about the specific system. We have simply said that there is ground state, first excited state, second excited state. In general, we will give you these kind of numbers and we will not ask you to calculate any of these states. There's one exception of a formula that is on our formula sheet, and that is worth discussing. And that is the energy levels of the hydrogen atom. Energy levels of the hydrogen atom follow a fairly straightforward formula, and that is each level is 13.6 electron volts times 1 over n squared. So let's draw this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if we take n equals 1, E1 would be a minus 13.6 electron volts. If we wanted to calculate what happens for n equals 2, we would have to take minus 13.6 electron volts times 1 divided by 2 squared. That happens to be 3.4. If we wanted to have the third level, we would take minus 13.6 electron volts by times 1 divided by 3 squared, that is 1.5. And we could maybe put one extra one on, but this one is starting to become tough. We have n equals 4, E4 equals minus 0.8 minus 0.9 electron volts, that is E4. So these are the energy levels of the hydrogen atom. How would one do an experiment in order to measure absorption? What one would do is one would have a light source. And this light source would send out light of all different colors that we want to test. And what I'm doing here is I'm going to draw the rainbow. We have already seen it's violet, blue, green, yellow, orange, and red. Then we're going to have a gas cell. And then there's going to be an observer over here who's going to look at what light they can see. If we assume, well, first I would like to note that if our gas is in the ground state and we are going all the way from the ground state to the first excited state, we have 10 electron volts. That is very deep UV light. So probably we're not going to work with hydrogen and the human eye. But for the sake of principle, I'm going to draw something over here that is visual so that I can use colored pencils. Let's say this gas absorbs green light, just for the sake of it, so that we have colors. What this means is that violet light travels through the gas, so the person can see violet light. It would mean that the blue light also travels through the gas, so the person could still see the blue. The yellow or orange light would make it through as well, as would the red light. However, the green light gets absorbed. All the energy that is carried by green photons would get absorbed by a gas that absorbs green. And so the person here would see no green light. This is called the effect of dark lines. So if you look through a gas and you see that you can see almost all the colors in the rainbow, but one kind of light is missing, that means that whatever was between you and a light source absorbed all the green light. Now, if we look over here at this diagram, we can try to see what kind of light would our hydrogen atom absorb. So the first kind of light that our hydrogen atom would absorb would be from level 1 to level 2. We would also absorb from level 1 to level 3. We would absorb from level 1 to level 4. We can calculate these. So if we wanted to know what E1 to 2 is, that would be 13.6 electron volts times 1 divided by 1 square minus 1 divided by 2 squared. If we wanted to calculate what the energy is for going from 1 to 3, you would say that's 13.6 electron volts times 1 divided by 1 square minus 1 divided by 3 squared E going from 1 to 4, that would be 13.6 electron volts times 1 divided by 1 square minus 1 divided by 4 square. What happens if we had light that had a bigger energy than 13.6 electron volts? So up here I have energy level of 0. What happens if we have light that has an energy that's bigger than 13.6 electron volts? It turns out we can actually rip electrons out of the atom. So for E photon greater than E1, the process of ripping electrons out of an atom is called ionization. So if we provide, if we, for instance, provide light with an energy of 15 electron volts, what we could do is we could take this electron from a bound state inside the atom and lift it all the way up above the 0 energy level. However, we know that if we go above 0 energy for a system, we cross from a bound state into an unbound state. And what this means for an atom is that we ripped an electron out of the atom. We ionized the atom. So, to summarize what we have learned until now, we have learned until now that the energy inside an atom, the electronic energy of electrons inside atoms, is quantized in discrete levels. Sending out light and absorbing light can only happen in discrete energy packets called photons. If we want to figure out what kind of light gets emitted by an atom, we need to know the initial state of the electron, and then the light that it gets emitted by the atom are all those energies, or correspond to all of these energies, which take us from the excited state to the ground state. We can have also pathways where we first go from the excited state that we have initially populated, we jump to an intermediate state, and then we go from this intermediate state all the way to the ground state. The energies can be calculated as the differences of the atomic energy levels. We have learned that in a cold atom normally sits in its ground state, and we can absorb light from the ground state into these excited states. We have learned that this absorption can only happen if the incoming photon is exactly resonant with the difference of the energy levels inside our atom. We have seen that this would give us dark lines, so lines of light get filtered out. We've learned about the energy levels of the hydrogen atom. There's a formula that will be on your formula sheet. And we have learned that if we provide energy that is bigger than the binding energy of the electron, bigger than negative the ground state of the system, that we can ionize atoms and we can take the electrons out of the system. After the initial push of developing quantum mechanics based on light and the discrete energy packets of photons, physicists figured out that energy quantization is something that is universal. A very important kind of energy quantization for our next chapter is the quantization of vibrational energy. So let's see what that looks like. We had already seen that the potential energy of an atomic spring can be approximated by a parabola, and that we can ascribe some kind of binding energy of this molecule falling apart to the bottom of our potential energy landscape. What quantum mechanics tells us is that atoms can emit energy in discrete packets. For vibration energy, these are labeled as levels 1, 0, 2, 3, 4, and so on and so forth. 0 is called the ground state. 1 is the first excited state, and so on and so forth. The distance between these lines is always exactly the same. That distance happens to be h bar times omega. What are these two things? Omega is the oscillation frequency of an oscillator, which we had already seen is spring constant divided by mass. There's nothing new here. H bar is the reduced Planck constant It's named after Max Planck, who is the person who first proposed that energy should be quantized. It turns out that later on in his life he wasn't particularly happy about what he proposed, but the name stuck because he invented the whole concept of that light should occur only in quantized packets. It turns out that this unit is incredibly small. 6.6 times 10 to the minus 34 joule seconds. Thus, if you have a macroscopic spring and it changes its energy in terms of these tiny little energy units, nobody is going to notice anything. However, if you have a molecular spring, then suddenly these small units of h bar omega are going to make themselves known. From quantum mechanics, one can actually find out where these energy levels are. The surprising thing is that the lowest energy level is not exactly at the bottom of our potential well. Rather, we take the bottom of our potential well and we have to add 1/2 to the bottom in order to obtain the correct energy levels. Now we have to, I want to come to the point of why is this important for the next chapter, which has to do with temperature. We will see that these energy changes here are rather small. So energy changes for vibrational energy levels are on the order of 10 millielectron volts. So that is about 100 times smaller than the energy changes that we saw for visible light. For visible light, we had said that a molecule at room temperature, or a cold molecule in general, will be always in its ground state. That is not true for vibrational energy. Because these energies are so small, we are still going to have the majority of atoms or molecules be in the ground state, but we're going to also have a few atoms or molecules in a gas be in the excited states. If we want to measure directly these vibrational energies, we have to be a little bit more sophisticated than we had been for the electronic energy levels, because we cannot see vibrations, but we can see how the vibrations change the optical spectrum of emission. So for that, I have here a figure from a paper. So let me walk you through this thing. On the bottom, we have the energy diagram, and there are two electronic states here. We have the top electronic state, which is the C3 pi U state, and we have the bottom electronic state, which is the B3 pi G state. Don't worry what these things mean. Each one of these electronic states has associated with it vibronic or vibrational substates. The system starts on top, that is the excited electronic state, but some of the atoms are in the ground state, in the nu prime equals 0 state. Some are the first excited state, some are the second excited state. When the system emits light by jumping into the lower half, light can either be emitted by jumping from the vibrational ground state to the vibrational ground state, or from the vibrational ground state to the first excited state vibrational, or from the vibrational ground state to a second vibrational state. Let's scroll up to the spectrum. So it's a little bit of a mess, I agree. So, but the good people here have done the job for us of labeling it. So they have here the peak that comes from transitioning from the electronic first excited state to electronic ground state, from vibrational state 0 to vibrational state 0. That has the highest, this has the highest energy or the lowest wavelength. If we go from the vibrational ground state to the first vibrational excited state, we get this peak. If we go from the ground state to the second excited vibrational state, we get that peak. So you see that these peaks are evenly spaced, just the way that quantum mechanics would tell us. But this is a right royal mess, and so we shall use our vibrational energies mostly in the next chapter to understand temperature. So with that, what do we have? We have learned that energy is quantized. All kinds of energy are quantized. We can see quantized electronic energy as the different energies of light that come out of an atom or that can be absorbed by an atom. And we have seen that the vibrational energy inside an atom is quantized as well.